So we were talking about these aqueous solutions that contained a small number of hydronium ions and hydroxide ions because of that self-ionization of water, which we had looked at to give the ion product. We had said, there we are. We had said that molecules of water can act as a base or an acid and exchange a proton to produce these hydronium ions and hydroxide ions. Concentration was small, but the concentration of the two ions combined was always constant. That gave us a Kw, the ion product of water, and it's really just the equilibrium constant for that self-ionization of water. That constant value was 1 times 10, excuse me, those peanuts were very salty I just had, 1 times 10 to the minus 14. And so if the hydronium ion concentration increased, to keep that constant, the hydroxide ion concentration would be decreasing. Or if the hydroxide ion concentration was increasing, the hydronium ion concentration must be decreasing to keep that constant a constant. And so we had said that we really only need to track one of the two ions, because if one is rising, we know the other's falling. And the decision was made to track pH, or the negative log of hydronium ions. And we said that the smaller the value, let's see, get back to my table, the smaller the value, the more acidic the solution, because of a high concentration of hydronium ions. But as pH started to rise, the hydronium ion concentration was decreasing and the hydroxide ion concentration was increasing until we had virtually all hydroxide ions and almost no hydronium ions at pH 14. And the pH 7 was our point of equivalence, where we had an equal concentration of hydronium ions and hydroxide ions. And we said that we could measure the pH of even a basic solution because we have this relationship that pH plus pOH is equal to 14. So we can work out the negative log of hydroxide ions for the pOH, and then pH would be 14 minus the pOH. That is where we had got to on a Monday. So if we look at a couple of examples that we can work out, excuse me. Eight people today, that must be very close to a record. Okay, so we look and ask ourselves, first of all, most importantly, do we have an acid or a base? And H2SO4 is one of our diprotic acids. Remember we said as a basic rule, if the chemical starts with hydrogen, then it's probably an acid. Although the H2SO4, the sulfuric acid, is specifically in our notes as one of our examples of a diprotic acid. And so that sulfuric acid, H2SO4, isn't just giving away one proton in water, it can give away two protons, which will need two molecules of water, dissociates fully because it's a strong acid. And so we produce two hydronium ions, and then we get the conjugate of the acid, the SO4, the sulfate, which we know as a stable ion from chapter 3 chemistry. And so the important thing here is that the concentration of the acid needs to be doubled to give us a concentration of hydronium ions in the solution. So that concentration for the acid needs to be doubled. So that 4.12 times 10 to the negative 3 multiplied by 2, that would become 8.24 times 10 to the negative 3. That's going to be the concentration of hydronium ions specifically. And so we'll take the negative log of that concentration. And I need my calculator for that because I'm not doing that in my head today. That looks like it comes to 2.08 for the pH. Oops, lost my pen. pH, because we were taking the negative log of hydronium ions, which is double the concentration of the original acid, because we've got a strong diprotic acid, giving away 2 protons each time. Any questions about that one? So we know it's an acid. We can directly calculate the hydronium ion log and pH. But just keep in mind that it's one of our 2 examples of a diprotic acid. If we look at the second one, 6.90 times 10 to the negative 3 molarity for sodium hydroxide. Of course, our hydroxide containing compounds are bases. Again, that rough check finishes with a proton in the formula. It's probably a base. Remember, there will be exceptions to that rule, but if you're really, really stuck, that's a good starting point. Okay. So sodium hydroxide is one of our strong bases. It dissociates in water completely into sodium ions and hydroxide ions. And so for every unit, every molecule of the base, there's one hydroxide ion produced. So the concentration of the base is also the concentration of hydroxide ions in solution too, or at least very, very close to it, because it almost fully dissociates sodium hydroxide. So we can take the negative log of the base, 6.9 times 10 to the negative 3. This time we get an answer of 2.16. But of course, this is the negative log of hydroxide ions. So this is POH, not pH. We can only calculate pH directly with the hydronium ion concentration. That's not the same thing, hydroxide ions. But we do have this rule that pH plus POH is equal to 14. So pH is equal to 14 minus the POH, which would be 14 minus the 2.16. And that gives us 11.84, looks like. If it's a basic solution, it should be a pH above 7. Don't be fooled by that initial answer of 2.16. That's POH, not pH. We only need this additional step if we're dealing with basic solutions. Okay, I have to clear the screen at this point. Then we've got a third one at the bottom. So this time 4.26 times 10 to the negative 4 for calcium hydroxide. And of course, calcium hydroxide is a base, fairly strong. It almost fully dissociates in water into calcium ions and hydroxide ions. So for every molecule of this base, it's producing 2 units of hydroxide ions. You can see it there in the formula. So this concentration for the base has to be doubled before it can give us the concentration of hydroxide ions specifically. That would be 8.52 times 10 to the negative 4. That's the concentration we take the negative log of. Excuse me. So let's calculate that. 8.52 and a negative log. So it looks like it comes to 3.07. But of course that's POH. So again, pH plus POH is equal to 14. pH will be 14 minus POH. And so that's 14 minus the 3.07. And so we get a value of 10.93 for pH. Any question about that one? We're doing okay? All right. Let's see, what have we got next? Can this possibly get any more exciting? Aha, titrations, which was a lab on Monday afternoon. Hope that wasn't too painful with a brand new lab procedure. It looked like from everybody's results that it worked fairly well. And after we'd spent half an hour just blahing about it, which wasn't too long. It looks like people were done in about 2 hours, so good. So we often come across solutions which have an unknown concentration. That could be an acid or a base. In order to work with them and use them, we need to know what that concentration is. And we can work out that concentration using a titration. Remember we said that at pH 7, the concentration of hydronium ions matches the concentration of hydroxide ions at pH 7. So if we can take an acid-base reaction to pH 7, we can work out the concentration of that unknown analyte, as it's called. So you've got the acid in this case. It could be a base that we're titrating, but if it's an acid, as in this case, what we call the analyte, that analyte is slowly neutralized by adding in base from a burette, the sodium hydroxide base, in this instance being known as the titrant. Of course, this looks very familiar. You've just got your Erlenmeyer with your acid in there, and adding in from the burette is your base to neutralize it. Sometimes you'd use a pH meter to know when you hit that pH 7, But sometimes you'd use a pH indicator, which we'll talk about in a second. Oh, I put the scale down here. So pH 7, that's what we're trying to hit. So you'll start adding in some base to the acid, and you'll see pH start to slowly rise. And this is because you've got a large volume of that acid in the beaker, and you're only adding drops, drop-wise, from the burette. So that's a very small amount of base at a time, and so a very small change in the acidity of the solution. But it will start to rise as we use up that acid and decrease the hydronium ion concentration. As more time passes and those hydronium ions from the analyte get neutralized by the titrant, the hydroxide, to produce water, we'll eventually reach a point where the majority of the hydronium ions have been used up or neutralized. So now as we make drop-wise additions of the base, now we start to see a very dramatic rise in pH because we've got very little of the hydronium ions left. So the addition of titrant, the addition of base is significant compared to that small amount of acid. So sometimes to recognize that pH reaching 7, we add in a small amount of phenolphthalein indicator or some other pH indicator. And the indicator is basically just an acid itself. This is a slightly simplified picture of the molecule. Remember, as we said in chapter 8, the lines are representing carbon to carbon bonds. So we've got these 6-membered carbon rings, 1, 2, 3 of them. And if there are any non-carbon, non-hydrogen atoms in the molecule, then we start to point them out. So there's a couple of oxygens in there as well. But very importantly, we've got this polar covalent oxygen to hydrogen bond. And these polarized bonds are bonds which are easy to break. And so once the acid in the beaker, the titrant has been used up, the analyte has been used up, the only acid left in the beaker is the indicator. So the sodium hydroxide will start to take hydrogens, protons, off the indicator instead. It's a very weak acid, so it's always the last to go. And as it becomes deprotonated, it turns into this ion form, which is brightly colored. pH about 9 for the full transformation, and it gives this bright pink color. So once the hydronium ions are used up, and we start using up the indicator, we see that pink color appear, and we know we've reached our titration point. Now, of course, we're aiming for pH 7, not pH 9, but the change in pH around the equivalence point is very dramatic. As we said, we started to turn the corner as we had very little of the acid, the analyte left. And with a very small amount of base addition, we see this incredibly dramatic change in pH. So we hit our target pH 7, and for perhaps just maybe a drop or two more, we hit that color change through the phenolphthalein. Different indicators will give a change in color at different pHs. Some are slightly above 7, some are slightly below 7, like methyl red and methyl orange. So we're pretty close to the point, so a very small amount of error there. And so we can take that color change as being very close to the actual point of equivalence. Remember, the point of equivalence, the moles of acid, those hydronium ions, equal the moles of base, the hydroxide ions. We know the concentration of that titrant, that base that was added. We know the volume because we can read it off the burette. And so we can work out how many moles of base, sodium hydroxide, were added. Because molarity times the volume in liters gives us a number of moles. And that figure we get for the moles of base must also be the moles of acid. We can then use that equation to work out the molarity of the acid. Remember, moles is equal to molarity times volume. So the molarity of the acid times its volume is equal to the molarity of the base times its volume. We know the number of moles of the acid. We know the number of moles of the acid. And so we can use the fact that molarity is equal to moles divided by volume to work out the molarity. Let's look at a couple of examples of titrations that are being performed. The ones in our lab are pretty straightforward because it's monoprotic acids which are reacting. So there's no trickery, which we'll see in a second. So titration performed with 300 milliliters of hydrochloric acid, and it's neutralized by just 25 milliliters of 6 molarity sodium hydroxide. What is the concentration of the acid? So as we look at the equation, 1 mole of sodium hydroxide reacts with 1 mole of hydrochloric acid to form water and salt. So for every mole of hydroxide ions, we need a mole of these hydrogen ions or hydronium ions. And so it's a 1-to-1 ratio. That's important. And at that pH 7, the moles of acid should be equal to the moles of base. We calculate the moles by taking the molarity times the volume. So the molarity times volume of the acid will be equal to the molarity times volume of the base because the moles are equal, and we calculate it like this. We can put in our values. We've got 300 milliliters of the acid solution. We have got 25 milliliters of the base, and the concentration of the base was 6 molarity. So for the molarity of the acid, 6 times 25 divided by 300, and that comes to a concentration of 0.5 molarity for the hydrochloric acid. Second one, a little bit trickier because we're now dealing with a diprotic acid that can give away 2 protons. As we've seen before, that H2SO4 will therefore need to react with 2 molecules of the base, the sodium hydroxide, because our acid is basically twice the strength. It will produce water and a salt, sodium sulfate, the leftover bits of the acid. When we take out the hydroxide ions, take out the hydrogen ions, sodium and sulfate, that's our leftover product. So the acid side needs to be multiplied by 2 to take into account the fact that it's a diprotic acid. So again, moles of acid should equal moles of base. We work out moles by taking the molarity times the volume. So we get the molarity of the acid times its volume is equal to the molarity of the base times its volume. We can plug in our values. We've got 200 milliliters of the acid. And normally for moles, we should convert to liters, but we can leave as milliliters as long as the base volume is left in milliliters as well. That will write itself. We've got 160 milliliters of the base being used, and the concentration of the base was 4 molarity. So for the molarity of the acid, we move that 200 across. It's a multiplier becoming a divider, and a 2. It's a multiplier on the left, so it becomes a divider on the right. So 4 times 160 divided by the 2 times 200, that comes to a molarity of 1.6. Any questions about those ones? We're sure? We're perfectly fine. There are no silly questions. Keep that in mind.
I don't know.
Do you have a question, Harrison?
No, I'm saying I don't know. I can't think of anything at the moment.
Okay, let's clear this up. Let's see what else we got. Did I do another one? Aha, here's one we can join in and do for ourselves. So calculate the concentration of 400 milliliters of barium hydroxide. So we've got the base, the barium hydroxide as the analyte this time, and it's the hydrochloric acid as the titrant. We use 500 milliliters of 2 molarity hydrochloric acid to neutralize the barium hydroxide. What's the concentration of the barium hydroxide? Take a couple of minutes and try that one for yourself, and we'll go over our answer, and that might be a good point to stop today, even though it's early. Otherwise we'll leave ourselves with not much to do on Friday. And it would be good to take a break before we hit buffers. That's usually the trickiest part of the chapter. Right, one sec. Okay, so one question in notes here about handing in the lab book. So people can hand in the lab book anytime this week. If I'm not around, just put it under my door in G104C. Let's see, if you can't hand it in before Thanksgiving break, what I had to do with my summer class, which was completely online, was get them to take photographs of their lab book or particular experiments with the lab notes for me to kind of just look over. But yeah, try and get your lab book in before the end of the week. Make sure you put your name on the lab book. Almost every semester, multiple people do not put their name on their lab book, and so I can't give them a grade. And that's 10% of your final grade, the lab book. Okay.
So what about the experiments that like I wasn't able to be in lab for these last few days?
Well, if you weren't in the lab, you wouldn't have any lab notes. Yeah.
Yeah, I mean, yeah, I get that, but like, I just want to double check on that.
So just hand in your lab book as is. I don't expect any lab notes if you've been quarantined and you've um, been doing those makeup assignments. There's no note taking assumed for those.
Okay, thanks.
Okay, but do not forget to hand in your lab book or submit it to me in some form. That is 10% of your grade. Okay, let's look at this last one. I think that will be a good point to stop. And we'll get into buffers on Friday. That's good. That gives us plenty of time after Thanksgiving to take a look at nuclear chemistry, usually a single period gets us finished for that. And we'll have plenty of time for practice. During that lab time on Monday afternoon after Thanksgiving break, we will do something together on Zoom, probably just some practice problems for acid-base chemistry or something. And even then, we certainly won't spend the whole 3 hours doing practice problems that would just drive people insane. So let's take a look. We've got, of course, this idea that the hydronium ion concentration combined should be equal to the hydroxide ion concentration combined at pH 7. And so that's moles of hydronium ions equal to moles of hydroxide ions. And we calculate the moles by taking the molarity times the volume. So molarity of the acid times the volume of the acid will be equal to the number of moles of acid. Likewise, the molarity of the base multiplied by the volume of the base will be equal to the number of moles of base. And they should be equal to each other at pH 7. So let's see, on the base side, we've got 400 milliliters. And we're trying to work out the concentration, so MB is what we're after. We have neutralized it with 500 milliliters of the acid. And the acid strength was just 2 molarity. But of course, the base, for every molecule, is producing 2 hydroxide ions, which is why we need 2 molecules of the acid. So that double strength for the base has to be taken into account. And we multiply the base side by 2 this time. So we're getting 2 hydroxides per molecule. So it's going to double the number of moles. So as we rearrange this, we'll move those across. So we get 2 times 500 divided by 400 times 2. The 2's will cancel. And so basically 500 divided by 400, that should come to 1.25. So molarity of the barium hydroxide, 1.25. Any questions about that one? So be careful with the potency of either the acid or the base with these titration problems. If it's one of our examples of a diprotic acid, you'd have to multiply the acid side by 2. Or if it was a triprotic, you'd multiply the acid side by 3. If it's a base using a group 1 metal, it's only going to produce 1 hydroxide ion each time, so that's fine. But if it's a base using a group 2 metal like barium or magnesium or calcium, then that's producing 2 hydroxide ions each time. You have to multiply the base side by 2. Okay. Quiet as mice. Right, I'll stop there. Looks like we're pretty close to time anyway. Yep, so only a little bit early. And then we'll finish the chapter on Friday. Let's see, I'm going to have a new grade up by some point today, a new current grade. You'll know I'm close to posting that up when I get up the polling question scores for chapter 7 and chapter 8. I'm working on them just now. So once they go up, you can expect the actual current grade to go up sometime soon. That will definitely happen today, even if I have to stay up till 2 o'clock in the morning to get it done. But I don't expect it to be that late. Probably 4 or 5 o'clock today, I would imagine, is when it will happen. And then within the next day or two, before the end of the week, polling questions will go up for acid-base chemistry, and the homework questions will go up for acid-base chemistry, but they won't be due until the Tuesday and Wednesday after we come back from Thanksgiving. So they will be up for 2 full weeks. Okay, right. Have a good day, guys. I'll talk to everybody soon. And with that, everybody left Dr. Elliott all alone.
Hey, Dr. Elliott.
Oh, hello.
Hey, it's me, Maria. I sent you my my lab report, the 12, just to make sure you got it.
That will be fine. Yeah, I saw my phone beeping. That will be fine.
Okay. All right. Thank you.
Okay. Good day. Bye.
Bye.
Also, Dr. Elliott, on Friday, my parents are coming to take me home.
That's all right. You just catch up with the lecture online because
Okay, thank you.
there's a kind of like a version of the what we did in class goes up. One sec. think my daughter's patience has run out. So you can just
Okay.
catch up with that particular online lecture.
All right, thanks.